Welcome to another problem session for preparing for JEE and MCAT. And so we're doing some a little bit harder problems, and they show up every now and then, and it's kind of a trick, you know. So before I go on to the solution, let me remind you to subscribe to this channel if you want to get some kind of notification. Okay. And you may want to check out my my website. That's a physics bootcamp.org. There are a lot more over there. As if it's the entire book. Okay. All right. So let me see what the problem is. So here's a block, and it's on a wedge. So this is wedge, and this is block. Both are moving, and other objects are there, but like it's on a table, all those things don't matter. Okay. So this is the only thing that's, and what's given is the wedge itself. So this structure itself has an acceleration a. Doesn't mean this has acceleration a. Okay. It's not only it's going along with the block, but along this inclined surface, it also is sliding. Okay. So this can slide. So we did a problem yesterday where the acceleration of the wedge was upward, and today we're going to do it, acceleration is horizontal. All right, so we want to find the acceleration. And today I also want to say this theta is 45 degrees for simplicity. You know, all the numbers will come out nicely. The m doesn't have to be given, but m will cancel out from the problem, so I don't have to give you. And it is at the top at t equals 0. T equals 0 at the top, and v equals 0 at t equal to 0 for the block. So it was at rest nicely and suddenly accelerated, and okay, so that is I'm going to give you, so you can easy to do the numericals. So giving this, we want to find where it will be, where at some arbitrary time t, and it can be done. Okay, so let's do this and then do this. So maybe do this first and then do this. Okay, so if you want to do it, go ahead, pause the video and kind of work it out for yourself. Let me move my all right, so give you a chance to pause. All right, let's do it. So it is a constraint problem. So let me say I'm going to use an inertial frame. Because we are doing this, that means I know in several bridges I've said this F equals to ma is only true, this form of the equation valid only with respect to an inertial frame. And somehow inertial frame defined where this is true. Okay, so you can do like a backward forward. So you can say if I have inertial frame, this will be the valid, and if this is valid, then the frame is inertial. So it's kind of like a backward forward. So it just F equals to ma is true if and only have inertial frame. And if you have inertial frame, then this is valid. All right. So inertial frame, it says if no force, then no acceleration. But because this is accelerating, and there may be force involved before that, but if I attach a frame to this acceleration will go to 0, because with respect to that acceleration, the wedge will not be accelerating. So if I were to say, hey, I'm going to do something like this, I'm going to do like this, and this will move with the wedge. So this is attached to the wedge. This will be some kind of attached to the wedge frame. In that frame, this equation will not be valid. So you may not use this. You have to modify this, and then you can use it. So that won't look like F equals ma. There will be more terms, and I'm not going to do that here, what those terms will be. You can go here. There's a discussion of that type of frame, okay? So maybe at t equal to 0, it was at t equal to 0, it was like this. But at some arbitrary time t, so this arbitrary time t, it will be over here. And the block was here at t equal to 0, but the block will be here at t. All right. So if I write this guy's coordinate as x and y, so don't need to worry about it. So these will be function of time, and this will be functions of time. And because this wedge is moving, I might say this point of the wedge, it has x, so that will be, and this will be a function of time. Well, clearly this angle is constant, though. So see, if I can look in this triangle, then this, let's call it height, and this part I'm going to call it width. So if I take h, now h will be changing. H will be a function of time, and this distance will be a function of time. But their ratio will be equals to tangent theta. So this is our constraint. And that will make these guys not independent. So let me try to draw a bigger picture some nicely. So from here to here, this whole thing, let's call it B, and we are over here. So this is Y, and this part is X. But from here to here, let's call it okay, from here all the way here is little x. So this little part will be x minus big X. And so this part, which we are calling WT, is B minus X minus X, which is B minus X plus big X. So this equation here is Y over B minus little x plus capital X equals to tangent theta. And so you can write this down. y equals to b tangent theta minus x tangent theta plus capital X tangent theta. We did this in the last video. So if I take a one-time derivative, I'm going to have a Vy. This will be 0. Vx tangent theta plus capital V, this for the wedge, x tangent theta. And do one more ddt minus ax tangent theta plus ax tangent theta, and this we are calling is a. Missing is moving, its acceleration is pointed to the right for convenience, okay? So this just becomes ay minus ax plus a. So this comes from the constraint that we found in the coordinates themselves. When you kind of have a rotation problems and the constraints sometimes there, something's rolling, usually you'll have a incremental instead of y, x, things like that. You might get a little increment. And so constraint may be in the velocity, you know. So like if something moving in a circle, angular velocity is related to the linear speed along the circle, right? So that's a constraint. So you've seen constraints, not like a new thing you're saying. So if something was moving in a circle, so you say, hey, in the circle, it moved this angle, it is distance ds, and this angle it moved was d theta in amount d time. So basically you're giving me speed relations, okay? So in that way, what you have is, but arc is, if this is r, then ds is r d theta, and then if you divide by dt, then this v equals to r omega. This we call omega for that guy, angular velocity. So this you have seen in another context. Those are this is a constraint in a circle motion. So the constraint can come up in many different ways. Here our constraint comes up this way. Okay. I see my this thing is not highlighting. I'm going to stop it and redo the highlight. Okay. So at this point, let me stop this. I'll fix the cursor so you can see the cursor better where my cursor is going. Okay, so that's my constraint. And now I need to write equation. You can see that I will get ay and ax, and this is known. This is known. And so I don't have to solve for both of them. I can solve for just ax and get ay from there. So how do I get, I need to set up, so f equals ma in this. We can draw another picture if we like. Yeah, let's draw it out. So here's the block at some arbitrary instant. Forces on the block. And we're assuming there's frictionless. That would mean there's no force along the wedge. The only force is a pushing normal 90 degrees. It is pushing, and you can just call it n. And then there is a gravity which is straight down, which is little, its mass is little m, We just assume that, not given, but you assume that. And this is theta. So this is 90 minus theta, but this whole thing is 90. This part is 90 minus theta. So this part will have to be theta. Okay. And the coordinate axis, or all I need is orientation. All you need is orientation. So this is along the x direction, along the y direction. And I don't have to assume the A is in this direction. Okay, mistake number one. Because it says the wedge is fixed. It will true if the wedge was fixed. So you can see at different times, it is down the wedge. It's down the wedge, but actually these variables ax and ay that you're looking at, this variable ax and ay, they will point some they will point so that this relation exists. Okay, this relation is satisfied. So we are just gonna have to do algebraically. It's better to get used to doing things algebraically rather than guessing around, because when you get to the quantum and more hard problems in physics, often the intuitive solution is not the way it goes. Intuition can come later, but first you need to focus on the algebraic aspect of the problem. All right. So here I need to separate so don't assume this and try to guess this is. So I'm going to have an x in that direction, y in that direction. It still will be this way because it's going to have. There's no way wherever the wedge is a particular direction in space. So when you work it out, it's going to be down the wedge, okay? But the wedge is going to be at different place. And having said that, let's do it out, okay? So I've got ax, max is going to be fx, and may is going to be fy. So what's going to be fx? This does not have any x component. The x is pointed this way. Only this kind of x component. So this is theta. Walk the theta to there. That's the theta. So the x part will be n sine theta. That part. So it's going to be n sine theta. Remember, I used to use fn for normal. You can always use n for normal, because if you're using n for normal and using numerical values, then n is also for Newton and can be very confusing. So if you're using numerical values, if all you're doing is symbolic, then it's better to use n, okay? Because it saves time and there's no scope of confusing getting. So that's n sine theta, and this one is going to be n cosine theta minus mg. Now, I'm not interested in finding n, so I will write this as may plus g, bring this on the other side and call it n cosine theta. And I can say 1 and 2, take a ratio of them. So I have 1 divided by 2, this over this. And this will be sine theta over cosine theta, because n cancelled out and m cancelled out. That's why I didn't need m, right? M was just kind of placeholder. So just doing this makes it as cosine theta equals to ay sine theta plus g sine theta. Now we already know AY is minus minus AX tan theta sine theta plus A tan theta sine theta plus G sine theta. Okay. Let's see, over here, going to simplify. So this whole thing will come sine square theta over cosine theta. This will become sine square theta over cosine theta, and say multiply by cosine theta everywhere. So AX cosine square theta equals minus AX sine square theta plus A sine square theta plus G sine theta cosine theta. Now you bring this over here, and this add to that becomes 1. So this AX is going to be A sine square theta plus G sine theta cosine theta. How about AY? So this is one answer. Another one will be AY is minus AX tan theta plus A tan theta. So AX is this, becomes minus A sine square. I'm not making algebra mistake. Tangent theta minus G sine theta cosine theta tangent theta plus A tangent theta. So between here and here, I can take A tangent theta common, and 1 minus sine square theta makes it cosine square theta, and this becomes G sine, and this becomes another sine theta, makes it sine square theta. So this one is just a one of the cosine. So you have A sine theta cosine theta minus G sine square theta. I think I'd gotten a different answer when I just did it earlier, so I'm not sure I made any mistakes here. So I think I had gotten earlier I got this, I get AX equals to G cosine square theta plus A sine square theta, and AY was A sine theta cosine theta minus G cosine square theta. So I had gotten this, but now I'm getting something else. I don't know what happened. Okay, because I got a different answer, then I'll basically let me do this again from here. This looks correct. This looks correct, and this G comes on the other side. That looks correct. So let's start from there again. So MAX equals to N sine theta MAY plus G equal to N cosine theta. So rather than repeat my previous way of doing things, let me do it. I will do it a little bit differently, because ay is already here. Divide this. So this is 2 and this is 1. So this time let's try to do 2 over 1. 2 over 1 is going to be, and tangent theta is coming, so this will ay plus g over ax, and the other side will be 1 over tangent theta, right? So we have a ay tangent theta plus g tangent theta equal to ax. So ay, I think ay is correct earlier. A tangent theta minus ax tangent theta. So this is a tangent theta minus ax tangent theta. Multiply these guys out. So I have a tangent square theta minus ax tangent square theta plus g tangent theta equals to ax. Now bring this on the other side. It's going to be 1 plus tangent square theta. So it must be sec square theta, right? So it's 1 plus sine square theta over cosine square theta. So this becomes sec square theta. So this just ax times sec square theta equals to a tangent square theta plus g tangent theta. So this is 1 over cosine square theta. So multiply them out. That gives me ax a tangent square theta cosine square theta plus g sine theta by cosine theta, for writing for that, times cosine square theta, and this will just become sine square theta. A sine square theta plus g sine theta cosine theta. Oh, so this was wrong. What I had done earlier was wrong, and just now what I did, this is correct. Now just complete it again. Okay, so ax equals to a tangent theta, ay equals theta minus ax tangent theta. So putting this ax, so this is correct. So ax is going to be this times that, a sine square theta plus g sine theta cosine theta. Let's write this as sine theta over cosine theta. So all right, so I've got a tangent theta. When you bring this with that, so this is sine theta over cosine theta. So you bring this with that. So a sine cube theta over cosine theta minus g sine square theta. They have sine theta, sine cosine kills it. So these guys, a over cosine theta common, take a sine theta, 1 minus sine square theta so this will become a cosine square theta, and this guy will kill this guy, and so it's going to be a sine theta cosine theta minus G sine squared theta. So I've got this also correct. All right. Oh, wow. So I was correct already and actually made a mistake when I was preparing for this thing. So AX was A sine squared theta plus G sine theta cosine theta, and AY is simply A sine theta cosine theta minus G sine squared theta. All right, that's the answer, but there were a couple numerical things we were going to do, and let's see quickly do it. All right, you know, it took me longer than it should have. So we from here we're saying theta equals to pi over 4. That means cosine theta is 1 over square root 2 is a sine theta. That's why the mistake I didn't catch, because the angle I worked with the pi over 4 and they're all kind of same. So from here and also A, I think I took A kind of convenient number, so everything is nice and simple later on. Yeah, let's also take A. I think I said let's try 2 meter per second square, and G equals to 10 meter per second square. So then AX is going to be 2 times 1 over half plus 10 times 1 over square root 2 times 1 over square root 2. So this is also large. So this is actually 1 plus 5 is 6 meter per second square, and AY is going to be 2 times, actually the 1 square root 2, that's also half, minus 10, that's also half. So 1 minus 5 equals to minus 4 meter per second square. So if you were to plot, it will be 6 here and 4 here, 6 here and 4 here. So in space, with respect to this coordinate, this is where the acceleration will be pointed. And the magnitude will be, square root of 6 square plus minus 4 square. We don't need to, if we're squaring it, 36 plus 16 so that's it's a little bit more than 7.1 or 2, okay? 7.2 maybe meter per second square, and it's in that direction, and you can figure out that angle. All right, so I got AX and AY. So AX is 6 meter per second square. This would just mean dVx dt is 6. That will means Vx at t minus Vx at 0 is 6t. Just integrate it. dVx equal to 6 dt. Integrate gives you that. And this is 0 for us. That's what it says, was at rest. So this will be Vx at any time is going to be 60. Similarly, AY equals to minus 4 means Vy at t is going to be minus 40. But this just means dx over dt is Vx, just means 60. So this will give me dx equal to 60 dt. Integrate these guys. So x at any time t minus x at 0 time equal to 6t square over 2, 0 to t, and so this just becomes that, and that's 3t square. So x at it was here at t equal to 0, right on the axis. Block was there, so x was x, so that means x at 0 is 0, but y at 0 is, let's call this height of the block h, is h. So this is 0, 3t square. So it will be at some point here, so where will be from here, this will be 3t square, and from here you should be able to show the y of t is equal to h minus 2t square. Okay, so it used to be, it would be here, but now it will be h, this is h, and now it's h minus 2t square. So that tells you the position. So if I give you h, you should, and give you t, so t equals to 2 seconds and h equals to, say, 20 meter, very tall. Okay, just absurd numbers. So x of t will be 3 times 2 square equals to, that means meter, and y of t equals to 20 meter minus 2 times 2 square. 20 minus 8 is also actually 12 meters. It's going to be, instead of 20 meters, it would have come down 8 meter. Okay, that's it for now, and I'm going to do some other problems in the future. Probably there's a problem coming up where if you want to do it, so later when I talk about it, this is the problem I have in mind. I was going to do it, but I ran out of time today. It's already too big a project. So acceleration is not given. Now, okay, so you find equation that gives the, so this is ax, ay is 0. So now you place this on a table, frictionless. So you find this guy's acceleration and this guy's acceleration. You find both of them at some time t. So you find equations if this guy has a block of mass m and this block of mass, and angle theta. The only thing given is theta. Theta is given. So can you set it up so you can find equations motions for both of these guys? Okay. All right, so that's what I'm going to do at some time in the future. It's a very good problem. It's a relatively hard problem, so I'm going to try to tackle it in another video. Okay, bye.